Today we are looking at the Unit 5 extension, The Matrix is a System. So our objective today is I can solve a system of linear equations using matrix row reduction in 2 out of 3 problems. So matrix row reduction is a new thing we'll be looking at today. It's yet another method of solving systems of equations. So very first, let's take a quick review of what matrix multiplication was. We haven't looked at this in quite a while. And we had this old story of Elvira, and Elvira's trying to supply the soccer team and the drama club with food and catering for their parties. And we had over here that the soccer team needs 8 chips, 7 cookies, and 4 drinks. And then we had different stores we could shop at. At Main Street Market, the cost of chips is $2, cost of cookies is $3, cost of drinks is $2. And we were asking ourselves, how can we figure out how much the soccer team would cost at Main Street Market? So how would we calculate that? How would you calculate how much the chips would cost? Well, we'd need to take the quantity of chips and multiply it by the cost. So 8 times 2 for the chips for the soccer team. And then we need to do the same thing with the cookies, 7 times 3. And of course we'd add that, right? Because the amount of the chips plus the amount of the cookies plus the amount of the drinks is the total amount. So we're going to add that 7 times 3. And then finally the cost of the drinks, 4 times 2. And that would equal 16 plus 21 plus 8, which is 45. Similarly, if we were to look at the drama club for Main Street Market, we'd do 10 times 2 plus 4 times 3 plus 4 times 2. So that's 20 plus 12 plus 8, which is 40. And after we do all the multiplications, because we could repeat that for the soccer club and Grandpa's grocery, drama club and Grandpa's grocery, we'd end up with a matrix, a 2 by 2 matrix. And this would be Main Street Market column, this would be Grandpa's grocery column, soccer team row, and drama club row. And these would be the total amounts we'd pay for each of these clubs at each of these grocery stores. So that's just a quick rundown of what we did with multiplication of matrices. A little bit different than multiplication of numbers. So let's take a look at this very particular matrix multiplication problem. Ignore this bit over here. Ignore everything after the equal sign. We're just looking right here at this matrix multiplication. What would we get if we multiplied those two matrices? Well, we're going to take 2 and x and multiply them together. And then we add 3 times y. So this is similar to like if these were chips and this was the cost of chips, we'd multiply those. And then cookies, amount of cookies, cost of cookies. Multiply those and then we add those together. That becomes our first row in our answer matrix. Similarly, we'll do that with the second row, 5x plus 1y. And that is our matrix. Remember, when we did analysis of the dimensions of matrix, this is a 2 by 2, 2 rows by 2 columns. This is a 2 row by 1 column. We said these inner dimensions needed to be the same, and the outer dimensions would determine what our result matrix was sized. So it would be 2 rows by 1 column. That's what we have here. This is one big entity in a single column. So we bring down our answers now. We can bring that along with us. And we get 2x plus 3y on the top, and that equals 10 on the top, and then 5x plus 1y, and that equals negative 1 on the bottom. Now question though, does this look at all familiar to you? Does this look like anything we've maybe been covering already? What if I scribbled out this matrix for just a second and I wrote curly braces instead? Does it start to look familiar now? This is a system of equations. This is this system of equations. It's written in a totally different way in these matrices here, but these represent the same problem. You can see this initial matrix is our coefficients. So here we've written both of these equations in standard form. Remember, standard form is ax plus by equals c. A, b, and c are all integers. We just took the coefficients of the variables and we put them into a matrix. And then we took the results, the numbers, and put them into a matrix on the other side of the equal sign. We set up this system of equations as a matrix problem. Now we can even simplify this notation a little bit more, because if you zoom in on this part right here of our matrix problem, this multiply by xy equals stuff, this is consistent in every two variable matrix problem. Any system of equations is going to have two variables. And so we know this part is always here. We don't actually have to write it. We can actually just understand that it's there and not have to write it every time, just take it out. One of the nice things about matrices is that we don't have so much to write all the time. So we can simplify it even more. Notice these numbers came down here and these numbers came down here. And we just took out all of this notation in the middle. So if we were to read this, we would say 2x plus 3y equals 10. There's sort of an understood equal sign there. There's a little understood x and a little understood y and a little add. Similarly, this would be 5x plus 1y equals negative 1. But we don't have to write all that stuff. We can just understand that it's there. So this is the first page on your assignment. And we're going to go through these together. Write these systems as matrices. Now this is one of the easiest pages you're ever going to do in homework on this class, because we're just going to take these numbers and put them in a matrix. Are you ready? So I see a number there, 16, then negative 4, then 4. Similarly, 2, 2, and negative 5. We just pulled the numbers out. And we know that these represent the same thing. This is 16x minus 4y equals 4. All right, so try the next one. Can you pull those numbers out? The top row is negative 2, 5, 12. The bottom row is a little bit trickier because there's an invisible 1 right there. But otherwise, we'll just take the numbers. 1, negative 3, negative 6. That's our matrix. That matrix represents that system of equations. All right, try the last one. Can you get it? Number, number, number. So 3, 2, 1. Again, there's an invisible 1 right here. So this is negative 1, negative 2, and negative 11. We need to make sure we bring those negatives along with us. So writing matrices from systems is just pulling the coefficients and the numbers out. So question, how should we interpret this matrix? Knowing what we know, right? We said this represents something in the form ax plus by equals c. What would this matrix mean? We've got some zeros in there, which is kind of weird. Well, let's just put this first one into standard form and see what we get. So we have 1 in place of a, so that's 1x, 0 in place of b, so 0y, and -1 in place of c, so equals -1. Well, we can simplify that. 1x is just x, and 0y is nothing, that's 0. So the left side just is left with x. And then x equals -1. So that's our x solution. That's telling us our x value. Similarly, on the second one, we have 0x plus 1y equals 4. This again becomes 0. This simplifies to y, and we have y equals 4. So this is a solution matrix. This is telling us the value of our solution. This is x equals -1, y equals 4. Or we often write that as a coordinate pair. -1, 4 is our solution. Now this is generally what solution matrices look like. They have 1s on the diagonal, and then there will be an extra column here with the value of the x, the value of the y. And then there are zeros otherwise. This is a fancy term called reduced row echelon form. You don't need to worry too much about what that means, except that means there are 1s on the diagonal, and we have this additional column with the variable answers. Now this is true even if there are more variables. Remember, systems of equations can have more than 2 equations. They can have more than 2 variables. They can have 3, they could have 4, they could have 100. But it would follow the same pattern. We'd still have 1s on the diagonal, zeros in the other spaces, and then an additional column with each of the variable answers. So here's the tricky part. This we know represents a system of equations. Right? This is 2x plus 3y equals 10, and 5x plus 1y equals -1. That's our system. That's what this matrix represents. This matrix over here represents x equals 1, y equals 4, or -1 rather. And this happens to be the solution to this system of equations. We know many ways of solving this, right? We know how to graph, we know how to substitute, we know elimination. But the question is, how do we do it with matrices? How do we get it from the problem to the solution? There's some magic matrix steps, except they're not magic at all. Actually, they're really just elimination. We've already been doing these. We're going to work on our elimination steps again, but we're going to do them as matrices this time. So here's what that looks like. We have some matrix solving rules we can use. First one is we can multiply or divide a row by a number. Remember, when we were doing elimination, we wanted to create opposites, right? So if we had like 5x plus 2y, and then we had like 3x plus y equals whatever equals 2. We wanted to multiply one of these equations by a number so it would create opposites when we added down. We'd get a -2y here, and then those would cancel. Same idea. We're looking to cancel terms in these matrices. And we can do that by multiplying or dividing an entire row by a number. Same thing as multiplying an entire equation by a number. Other things we can do, we can add or subtract 2 rows. Remember, that's exactly the same as adding straight down like we did in elimination. We can swap 2 rows. Now, we never did this in elimination. The only reason you want to do that in a matrix is because you want to get this format with the 1s on the diagonal. Sometimes you end up with them swapped, so they look like this, and then our brains are like, what? I don't get that. I don't understand what I'm looking at. So we just swap rows. That would be the same thing as swapping the order of these 2 equations. Of course you can do that. You can write equations in any order. They're still the same equations. And then our fourth step says, or our fourth option is we can combine any of these. So if we wanted to do more than one in a single step, we could do that. I know this is all abstract and kind of weird and difficult to understand. Let's just roll with it for a second and see an example. See if we can figure out how this applies to elimination, how they're similar. So here we have an example. We have this systems problem. First, let's imagine what this looks like as an actual system. 2x plus 3y equals 10, and 5x plus 1y equals negative 1. This is the example we've been looking at in the previous slides. This is what our system looks like. So what opportunity can you see for elimination? Can you see a chance to multiply one of these rows by something so that one of these variables will cancel? By the way, this is on your formative assignment, so you'll want to follow along there. What if we multiplied this second equation by negative 3? If we did that, this y would become a negative 3, that would be a positive 3, and they should cancel, right? So let's look at how we do that with matrices now, with this sort of simplified notation. I'm going to call this row 1 and row 2. We're just going to refer to those that way. And to multiply this second one by negative 3, I'm just going to say R2 times negative 3. So I haven't done anything to row 1. That's just going to come down right as it is, 2, 3, and 10. And now we're going to multiply each one of these terms by negative 3. 5 times negative 3 is negative 15. 1 times negative 3 is negative 3. Negative 1 times negative 3 is positive 3. So that's our resulting matrix, and now we can apply another step. If we were doing elimination, what we do here is add straight down, right? We're adding row 1 to row 2. So that's exactly what we're going to do. We're going to add row 1 to row 2 and try to get those y variables to eliminate. So 2, 3, and 10. So this first row, we're not doing anything with it again. We're just going to keep that exactly as it is. 2, 3, and 10. And then we're going to add these two together. 2 plus negative 15 is negative 13. 3 plus negative 3 is 0. 10 plus 3 is 13. So now we're getting zeros. Zeros are really helpful for us. We are trying to get zeros in these first two columns in a couple of places. So this row is starting to look a little bit like this one. This is starting to look like our x value. But can we do something now to this row to get this to be 1? That's what we want, right? We want a 1, a 0, and then a value. So how do we get this to be 1? Another way to think about this is if we wrote this in as an equation, this would be negative 13x 0y equals 13. We have negative 13x equals 13. How would you solve that? Well, we just divide by negative 13, right? We just divide both sides by negative 13, and we get x equals negative 1. We do the same thing. It's the same idea, same exact idea. We're going to divide that row by negative 13. R2 divided by negative 13. Again, we have not done anything with row 1 yet. It just keeps coming down with us. Now we're going to divide each of these terms by negative 13. Negative 13 divided by negative 13, that's just a positive 1. 0 divided by anything is 0. 13 divided by negative 13, that's negative 1. And look at that, 1, 0, negative 1. That tells us our x value. We already have our x value, x equals negative 1. Now we do tend to like to have our x value on top, so I'm going to swap these two rows. So after we swap, we get 1, 0, negative 1 on top, and then 2, 3, 10 on the bottom. So now we need to figure out how to get rid of this 2, right? We want it to be a 0. So we need to do something to get that to become a 0. We have the option of multiplying or dividing a row by a number, adding or subtracting 2 rows. Well, if we multiplied this equation by -2, we'd get a -2 there, and then those would cancel, right, if we added them together? So let's try that. Let's do R1 times -2. We're going to get 1 times -2 is -2. 0 times -2 is 0. -1 times -2. A negative times a negative is a positive, and 1 times 2 is 2, so it's +2. And everything in row 2 just comes straight down. Now we did go a little bit backwards there, right? We have an answer for x, but we can still get that answer back. It's not that hard. All we have to do now is just undo that operation we just did. We just have to divide that row by -2. We're doing that temporarily so that we can easily add straight down like we do in elimination. So our first row, I'm going to do R1 plus R2 here. That's our elimination step. My first row stays the same. I get -2, 0, and 2. And when we add straight down, -2 plus 2 is 0. 0 plus 3 is 3. 2 plus 10 is 12. So now we're so close to that form. We have zeros in the correct place, right? We have the zeros. Now we just need to turn these two numbers into ones. And all we need to do that is just divide by that number. We can take R1 divided by -2. That's going to give us -2 divided by -2 is +1. 0 divided by anything is 0. +2 divided by -2 is -1. You just bring row 2 down. So there's our x answer. Now all we have to do to get y is just divide this row by 3. We have to get this to a negative or to a +1. So we'll do R2 divided by 3 to get that to be 1. Our top row is the same. Then we have 0 divided by anything is 0. 3 divided by 3 is 1. 12 divided by 3 is 4. And that is our solution. We have x equals -1, y equals 4. Or sometimes we write that as a coordinate pair, right? If we were graphing this. Now this is what we would have gotten if we'd put this system of equations into Desmos as a graph, or if we'd solved a substitution, or if we solved with elimination. We have a different method now with matrices, which is a lot like elimination, but we don't have to write all the variables and the plus and the minus and the equal sign all in there. We're just doing matrix row operations. Should we look at Desmos and see that it does equal that? Let's put these two equations in Desmos and see. So here we are in Desmos, and I'm just going to type in those equations. Actually, I can lower this and you can see those equations right there. 2x plus 3y equals 10. 2x plus 3y equals 10. And then 5x plus 1y equals -1. 5x plus 1y equals -1. And we said that our answer should be -1, +4. So let's look. Where do they cross? -1, +4 right there. So we got the same answer using matrix row operations as we do in Desmos graphing. Let's try another example. Okay, we're going to try to solve this one, make it look like that solution matrix. Okay, so first thing we do is look for opportunities to cancel. Do you see any opportunities to cancel here? Either in that first column or in the second column. Yeah, absolutely. Those cancel already. We don't even have to multiply anything. We can just say like R1 plus R2. We can just add them straight down. Now, you'll notice previously I did this in the second row. You can replace the first or the second row, it doesn't matter. So I'm going to replace the first row in this case, just because I chose to. So 3 plus 1 is 4. Negative 2 plus 2 is 0. 18 plus 30 is 48. And then my second row just comes straight down. Now I've already got this first row sort of in this form, right? I've got this 1 now. How do I turn this 4 into a 1? How did we do it last time? Well, we just divided by 4, right? We can just take R1 divide by 4. And then we take each of these terms divided by 4. 4 divided by 4 is 1. 0 divided by anything is 0. 48 divided by 4 is 12. And we bring row 2 down. We already have our x value. How amazing is that? Our x value is 12. Now we just need to have the y value. We need to get rid of the x down here. Well, how about we just subtract this other one, right? If we just take R2 minus R1, those will cancel now. Those are already almost opposites. So let's do that. R2 minus R1. 1 minus 1. Well, actually, our first row we're not changing. We're going to keep our first row the same. Now 1 minus 1 is 0. 2 minus 0 is 2. 30 minus 12 is 18. Now we've got those zeros. All we have to do is get this 2 to be a 1. What do we do? What do we do to get that 2 to be a 1? Same thing we did up here. We just divide by 2. And we get 1, 0, 12. 0 divided by 2 is 0. 2 divided by 2 is 1. 18 divided by 2 is 9. So what is our answer? Well, our answer is 12, 9. Or we could write it as x equals 12, y equals 9. Again, you could verify this in Desmos. You could go over to Desmos, type in 3x minus 2y equals 18, 1x plus 2y equals 30, and see where it crosses. See if it crosses at 12, 9. So go ahead and give this one a try on your own. Pause the video, see if you can come up with a way to get this matrix to look like this matrix. You can combine two rows, you can multiply either row by a particular number. You're trying to create opposites so that you can eliminate one of the variables. This is our x, this is our y, and you're looking to eliminate one of them. Then come back after you've paused it, after you've given it a try, and see if we get the same answer. So it looks to me like we have a good opportunity for elimination right here. If we multiplied this by -2, we'd get a -4, and then those two would cancel. So that's what I'm going to start with. I'm going to do R2 times -2. We didn't do anything with R1, so I'm just going to leave that as it is. And then we have 2 times -2, -4. 3 times -2 is -6. 6 times -2 is -12. Now I can add these straight down. Again, we didn't change R1. When we add straight down, we're going to get 4 minus 4 is 0. 5 minus 6 is -1. 8 minus 12 is -4. All right, so now we have 1, 0. That's helpful. How would we change this to a positive 1? So we're very close to our y value here. We just need to change this to a positive 1 somehow. Oh, well, we just divide it by -1, right? R2 divided by -1, and that -1 will become a positive 1. So we didn't change row 1. 0 divided by anything is 0. -1 divided by -1 is positive 1. -4 divided by -1 is a positive 4. There's our y value. Our y value has come out. Now we just need to get our x value. So we're looking to do elimination here. What can we do to eliminate that 5? Well, what if we multiplied this one by -5? Then we'd get 5 plus -5, and those would go away, right? So let's try that. R2 times -5. We didn't change the first row. First row just comes over like normal. 4, 5, 8. Then we have 0 times -5 is 0. 1 times -5 is -5. 4 times -5 is -20. Now we're trying to get the x value up here, right? So we're going to add these straight down, but I'm going to replace this top one this time because we already got our y value down here. So when I add this straight down, we get 4 plus 0 is 4. 5 plus -5 is 0. 8 minus 20 is -12. And we didn't change row 2. We are so very close. We've got zeros in the correct place. We just need to fix each of these rows. So we need this to become a 1, and we need this to become a 1. So what do we do to make this a 1? We've done it a few times before. We did it here. We did it in previous problems. We can just do 4 divided by 4, right? We just do R1 divided by 4. So 4 divided by 4 is 1. 0 divided by 4 is 0. -12 divided by 4 is -3. And we didn't do anything to row 2. So now that top row is in the correct form. We've got x equals 3. Let's just look at our bottom one now. How do we get this -5 be 1? It's the exact same method. Yeah, we're going to take row 2 and divide it by -5. So our top row we have 1, 0, -3. Our bottom row we have 0 divided by -5 is 0. -5 divided by -5, that's a positive 1. And -20 divided by -5 is negative. Oh no, it's positive 4. Positive 4, there we go. So that is our answer. X is -3, y is positive 4, or we could write it as a coordinate pair. Now something cool, just really quick, is Desmos actually has a matrix calculator that I'll show you really quick. So this is the Desmos matrix calculator. It's different than their graphing calculator. It's also different than their scientific calculator. They have a few different kinds of calculators available on their website, and this is a specific one for matrices. But it's really cool. I'll show you how it works. We'll do this last problem that we did by hand. We just click New Matrix. And remember, ours was 3 columns, right? We had x value, y value, and then the number. So we actually need another column here. It just gives us 2 by 2 by default. I want to add another column. And now this looks more like the matrix we were working with. And our original matrix was 4, 5, 8, and then 2, 3, 6. All I do is I just type those in and press enter, and now it has defined matrix A for us. Remember, that is 4x plus 5y equals 8, 2x plus 3y equals 6. And the thing that is so super cool about this is it has this button, RREF. That stands for Reduced Row Echelon Form. We mentioned that a couple slides ago. That was the solution form of a matrix. So what this does is that we press that function key, the RREF, and we pass in our matrix. We pass in our matrix A. It actually calculates the solution for us automatically. So it just did all those steps that we did for us. It just solved that entire equation, says our answer is -3, positive 4, which you'll recall is what we got, -3, positive 4. So you can use the matrix calculator in Desmos to get to reduced row echelon form and solve systems of equations yet another awesome, fast way. So that's just a quick overview, a very quick overview of solving systems of equations in matrices. And that brings us back to our objective. Today's objective was, I can solve a system of linear equations using matrix row reduction in 2 out of 3 problems.